So I'd first like to begin my discussion on geometry by talking about Euclid and his elements, and specifically his postulates 1 through 5. Postulates 1 through 4 are very short, intuitive statements that we really learn in our early years of education, such as a line can be connected between 2 points, or a circle is described by its center and its radius. However, postulate 5 is very long, very confusing, and not intuitive whatsoever, and many argue it actually is can be derived from the previous four postulates and is rather a theorem than a postulate. Nevertheless, it does have a lot of implications, postulate 5, which today we consider Euclidean geometry. One of these important implications is that a triangle has 180 degrees, or its angles sum to two right angles. Following Euclidean geometry is analytic geometry, which is basically geometry with a heavy algebraic and equation-based focus, and this is different than Euclidean geometry and in its style of proof. This was really practiced by Fermat and Descartes, who both really possessed the fundamental understanding that that there's a connection between an algebraic equation and a corresponding curve. And Fermat was really able to state the equations of many common curves, such as parabolas or hyperbolas, but the only difference that he had with our current analytic geometry, which we call Cartesian or coordinate geometry, is that he only utilized one axis and generally only accepted positive solutions. So in today, he would be restricted to the first quadrant of the coordinate plane. Following this, in the 18th century, people once again tried to prove the parallel postulate, and Sacchieri and Lambert did this by first stating that the parallel postulate is false, and then proving by contradiction that it was true in the right angle case of a quadrilateral and not in an obtuse or an acute angle case. Both Sacchieri and Lambert had a great difficult time disproving the acute case in which the parallel postulate would not hold. And this led to a lot of implications, one of which Lambert discovered is that the defect of the area of a triangle is proportional to its area. And the defect is the difference between the sum of a triangle's angles and 180 degrees. And this is, of course, contradictory to the parallel postulate, which states that a triangle must have 180 degrees. However, with the parallel postulate for the first time not holding, this opens up many other areas of geometry. The most recognizable ones today are hyperbolic and spherical geometry, which have a lot of real-life applications, such as in spherical, the flight paths of planes, or in hyperbolic, the geometry of the internet. And I believe a problem that strongly demonstrates how the difference between Euclidean and non-Euclidean geometry when the parallel postulate does not hold is problem 3 of Catch Chapter 20. And flip this around.